Nat and I will be presenting that, but just as a note, we are just up here giving the talk. This is work done by several, let's say, generations of graduate students over the last couple of decades. So thanks to all of them. Um, so let me take a line from Dennis's presentation. I don't know if you guys caught that. So I'm a Lord of the Rings fan. So that caught my eye. So in one of the slides, Dennis has said that, in the kernel bind them, something like that. So that's a line from the Lord of the Rings, like one ring to rule them all, one ring to find them, so on and so forth. So a few years ago, we had a ambitious goal to see if we could bring together the myriad of MVAPICH versions under one umbrella. So over the last couple of years, Nat has been leading that effort, and that has led to the creation of the MVAPICH Plus MPI library, which has support for Intel, AMD, ARM CPUs, Intel, again, NVIDIA, ARM, like AMD, Intel GPUs, Omnipath, OPX, InfiniBand, Slingshot, Ethernet networks. So basically, that is the library which hopefully is going to rule them all, and at OSU bind them. So having said that, what is the MVAPICH MPI library? So we've been around for over a couple of decades, and we are a derivative of MPICH. We are available in different formats and versions, so you can download the source code openly. We can also give you RPMs or Docker containers. We are also available through SPAC and E4S. And this tutorial is going to be describing the various features of the MVAPICH MPI library and showing how you can extract the best performance out of it. So again, this is what I just described. We've been around for more than a couple of decades, and we have been powering a lot of HPC centers. And one unique thing about MVAPICH is that most of the development designs are done by students. Which is not the norm with other MPI distros like HPCX, OpenMPI, Intel MPI. So we are unique in that, and we are research driven. This is a high level architecture. This has been evolving over the last couple of decades. So just like the MPI library is able to support all the different kind of architectures underneath, we want the MPI library to be able to support all different programming models above as well. So in that regard, we want MVAPICH to be the common communication substrate for traditional MPI applications, your partition global address space applications, as well as emerging deep learning applications. And we are able to achieve that. And underneath, MVAPICH has support for a lot of modern networking technologies, as well as inter and intra-node communication mechanisms. One concern that people typically have with let's say university or let's say projects where students work on, say, what is the quality? Will my code work? Will it crash? Will it burn? Will it hang my system? So we ensure that these things don't happen, and we have some exhaustive and rigorous testing, and each commit goes over like 18,000 core hours. We have a lot of in-house tools and infrastructure for testing different commits. So this is a snapshot of what you see. We have a lot of different tests. This is how the summary of one test looks like, and each test have various different combinations. Now, all of you guys know that MPI libraries or any communication middleware will have a lot of knobs. So you saw Samir setting a lot of variables when he was running the profiling information with tau. So just like that, MVAPICH also has a lot of knobs, and we ensure that we test almost all the different possible combinations of these in our testing framework. So that's the functionality side. We also have extensive tests for performance to make sure that commit on commit, we don't degrade in terms of your performance. And we do run this on various local as well as national and international HPC systems to make sure that performance is better or equal to the previous release. As I mentioned, we have like various deployment versions. You can get our libraries as open source code in RPMs, in containers, through SPAC, whatever way you like it. So this is a basic workflow for SPAC solutions, and Matt Lieber, who's hanging out back there, is the master for the SPAC workflow here. And this is typically how you install the versions from SPAC from source. And additionally, the closed source versions are also available through different mirrors that you can add like this to the SPAC repository. So again, this gives you more details about the installation procedure, and more details of this are available in our quick start guide as well as detailed user guides. So what are our plans for the future? And some of these plans will also be shown in the upcoming slides, which we have been able to realize through various designs. We want to have good job startup, good point-to-point communication, good collective communication, and translating all of this to good application level performance. At a micro benchmark level, you might have seen a lot of marketing slides saying that, okay, I get 0.9 microseconds for like a 4-byte message size. But in most cases, that really doesn't matter. Your application has so much fat in it that you will not realize that 4 microseconds at the application level. At the application level, what really matters is whether you are using the correct communication protocol, the correct transport protocol. Are you using eager versus rendezvous? And these are some of the things that we'll be showing later on about how to translate your lower level benefits to application benefits. What are the best knobs to get there? How do you get overlap of computation and communication? So some of the slides that Rich Graham had shown about how you can use DPUs. So we have done a lot of those designs and taken that in, and we'll see some of those results here as well. And we have a bunch of other features, including energy awareness and how you can save energy in an application agnostic fashion without making any changes to the application. So with that, let me hand over to Nat. He's the lead developer for the MVAPICH project, and he will go over the various versions of MVAPICH and describe what each version supports. So Nat, if you want to take over.
Yep. So first off, to borrow again from an earlier presentation, there's not a whole lot of one-size-fits-all available in HPC. So we have a lot of different versions of MVAPICH available for different use cases and to support different environments. So our basic, as close to a one-size-fits-all version that you're going to find is our standard open source MVAPICH software stack. Now this provides all of our support for high performance interconnects and is going to have the most broad spectrum support. But we do also offer our MVAPICH 2X version, which is targeted at exascale systems and supports hybrid programming models as well as some advanced features that often require additional kernel modules or other more experimental concepts. And then we also have our MVAPICH 2 GDR software stack that is aimed at optimizing for GPU applications. And what we're currently working on is bringing both of those two enhanced stacks under the umbrella of MVAPICH Plus, which is going to include all of our optimizations, all of our cutting edge research, and everything that we're working on developing and enhancing. And then we will start to, as those designs become more widely accepted, easier to use, we'll start to move them into the open source version as we go. So the latest complete version of the MVAPICH open source software stack is MVAPICH 3.0. We released that in late February of this year. This is a big step forward for us based on MPICH 3.4.3, which is the latest available MPICH version on the MPI 3.1 standard. There's a lot more work going into getting us up to the latest MPI 4.1 standard that I'll get into later, but this is the final version on the 3.1 standard. This added support for all available networks through UCX and OFI netmods, which allow a user to build for either the OFI or the UCX substrate. UCX is, as most of you are probably familiar with, it's very good for IB systems, whereas OFI has really broad spectrum support for any type of network possible and has a lot of the upcoming high performance networks like Slingshot, like OPX included there. So now you don't have to worry about a whole bunch of different network substrates. You can just use OFI. It also has our enhanced collective designs that we've been building on for the past 20 years, and has improved CVARs included that allow for easier tuning and better maintainability. So I'm going to go over a couple features of the MVAPICH library. A lot of these have been in the software for a while, so this may be familiar to some of you, but they are very important for users of MVAPICH, folks doing application level tuning, to see what kind of available levers and knobs there are for us to improve performance. And these concepts are going to carry over into all versions of MVAPICH, even if they may come with slightly different names. So the first thing we're going to go over is process mapping support. So HPC applications can be really sensitive to how your MPI ranks are distributed across a node. So for instance, if you have something that's very heavily, very intranode heavy on communication, it is often better to keep a lot of your ranks close to each other on an individual node, trying to keep them within the same socket or NUMA domain so that you can optimize your intranode transfers. Whereas if you're doing something that is more dependent on intranode transfers, it may be better to spread those processes out so you can, for instance, take advantage of multiple HCAs on an individual node and having your processes located on the socket closest to the HCA that they're going to be using. So once again, there's no one size fits all here. This typically requires some knowledge of the communication patterns in your application and then what levers you have available to you in MVAPICH. So our default policy is going to be a spread policy, which will essentially allow each of your MPI ranks to take up as many cores as possible based on how many ranks you have assigned to the node, and we're going to bind that at the core level. But you can also change that based on if you want to, like I said, spread out your processes to keep them limited to, say, a single network adapter or a single GPU. And you can also change that from binding at the core level to binding to an individual socket and allow ranks to sort of context switch as needed across a socket or across a NUMA node. So we're going to take a look at some examples of that. So this first example shows the core binding, which, as I mentioned, is going to be our default binding. It's going to bind everything to a single physical core as opposed to a group of cores or hardware threads. And this is going to be a bunch mapping. So this is going to keep all of your ranks as close together as possible. This is going to be really nice if your processes are typically exchanging information with nearby ranks. You want to co-locate them on the same socket, all next to each other. This is a pretty good starting point. It's a good way to get a baseline and then experiment with other mapping policies. If we go then instead to a socket level bunch mapping, we are going to specifically bind everything on one socket. So it doesn't end up looking much different in this case, but what this will do for us is allow all four of our ranks on this socket to kind of float between the processors as needed. This can be nice if you have an application that's going to be blocking on I/O. They can kind of move around to the different cores as needed. You're not going to be as sensitive to something like system interrupts. We can also, scatter will divide your ranks evenly among the available compute resources. So if you scatter at the core level, it will divide your sockets and give you an even mapping of, or an even distribution of ranks to sockets, and then bind each of those ranks to a core. So why this is important to understand is to highlight the difference between core binding and a socket or NUMA node binding. The core binding specifically, as you can see here, is going to keep your ranks bound to a single core. Sometimes this is really good for avoiding resource contention, but sometimes this can also arbitrarily limit you if, for instance, you're binding to core 0, which is going to be used for operating system interrupts. In that case, if you have only 2 ranks on a socket with 4 cores, it may be better to allow them to float between the cores on that socket, and that's what the socket binding is going to give you. So one thing that MVAPICH supports that is really convenient is a hybrid binding model. So this allows you to mix and match MPI ranks with a threaded program. So you can have threads that are not within the confines of MPI if your application is threaded as well as using MPI. This will allow you to account for that, because if we look back at these binding policies, if I bound to core, my rank 0, even if it had 4 threads, would still only be allowed to execute on core 0. And that's obviously going to hinder performance if I'm trying to take advantage of multi-threading. So by having these environment variables that allow you to set multiple threads per process, you can account for an application that also takes advantage of threading. So we set this with our hybrid binding policy environment variable, and we have a couple main ways to do this. The first is going to be compact. So if your processors support hardware multi-threading, this will bind the threads to the hardware threads. So this isn't super common, at least in my experience. Most HPC centers do not enable hardware multi-threading on their processors because for most applications, it doesn't see that many benefits, and if your MPI is not aware of this, it can cause issues because you're getting multiple MPI ranks that expect to be their own processes bound to hardware threads, and that can cause issues. But if it is available, this compact binding can be really nice for making the most out of your available resources. And that's what this diagram here is showing. Your MPI rank will be assigned to a core, and in this case, each core has 4 available hardware threads, so we're going to bind the threads across those available hardware resources. On the other hand, a linear binding is going to ignore those hardware threads. It's going to stick to the cores. But what this does is essentially give you a step size that is going to allocate 4 cores to rank 0, allowing the threads of rank 0 to then be bound across these cores. And again, this is really nice. Most of the time, all the time, your threads are going to be working closely together. So it's best to keep them close to each other on the same or in co-located cores. So again, this is an example of binding the ranks to the NUMA node, and this is going to once again account for the threads, but do it at the NUMA node level. So the threads are going to be able to shift on the NUMA node more freely, and this again lets you free up resources if one processor is being taken up doing things like handling interrupts. For the really special cases, these preset bindings are going to cover probably the vast majority of cases, but for really specific cases, we do also offer a custom binding option. And this is done by just setting the CPU mapping, and you can set, it uses a colon-separated list to specifically assign each rank to an individual core ID. This can be nice if you have a really unique application, or if you just want to see the effects of binding to different cores, or to see, it's really nice for investigative purposes to narrow down if there's issues with a particular binding policy. And we can also debug this by using the show CPU binding flag to take a look at where our CPU and rank bindings are occurring. In the event that you are trying to run with something like Slurm or Flux, a lot of those use their own process binding. In that case, you can also disable the MVAPICH level process mapping entirely by setting enable affinity to 0. And that can be helpful to avoid conflicts between two different, your launcher and your library trying to bind against each other. All right, so moving on to collective communication. So we've done, over the last 20 years, the MVAPICH project has seen a lot of work in optimized collective communication because that is kind of the bedrock of MPI, right? Point-to-point communication will only get you so far, and we can leverage our knowledge of different networking technologies to enhance and improve the speed of collective communications. So your most basic naive algorithms are going to be what we call flat algorithms. Those aren't super interesting, so we're not going to spend a ton of time on them. Mostly what we do is related to optimizing our collectives for modern CPUs, which typically have lots of cores, multiple NUMA nodes, and those interact with the system in different ways. So one of the designs we have worked on is hardware multicast. So this shows numbers on TAC Frontera and the way we're able to perform a bcast operation with about 2 times improvement in latency when taking advantage of these features on the network adapter. So this is enabled by setting use MCAS to 1. Pretty nice and straightforward, and it can show pretty significant performance improvements for bcast and scatter operations. So once again, you can see, even scaling up to thousands of processes, we can show a performance gain of up to 75% for very small messages. So this is great if you have a lot of small messages in your application. This does need to be enabled at configure time, and then once it is enabled at the configure time, you can enable it at runtime as well. Typically, this will be enabled by default on most systems, so you never actually have to think about this. If your system supports it, we'll use it. Another feature of modern MVAPICH libraries is the SHARP protocol on NVIDIA Mellanox systems. So SHARP is a in-network compute model that allows for the offloading of common compute operations to the network hardware. So this lets you do your reductions on your switch instead of on your CPU, which is really nice for improving the performance of reduction-based collectives because you don't have to wait for those to be processed on the CPU. They can happen while they're in network. So you can see this, for blocking collectives, this can show anywhere for 5 to 9 times improvement. And there's a lot of enhancements we've done here. These were originally available only in MVAPICH 2x, but we have brought these into the open source version. SHARP is only supported on a few clusters. It does have to be enabled at the network level by the system administrator, but if it is available, it does show really excellent performance gains. Another feature of SHARP is streaming aggregation, which once again can improve performance of our reduction collectives even further. So this is our design with streaming aggregation, and you can see compared to our standard MVAPICH 2x design, it shows even further improvements. This, I believe, will be going into a future version of MVAPICH Plus. And then these are some performance results with the non-blocking collectives, which again, we can see 4 to 6 times performance improvement, and we can get a lot more overlap with our computation and communication. And then, because like Hari said, quite often those micro benchmark levels don't always translate to your application, we are able to see actually pretty significant performance gains at the application level on the order of about 12%. Once again, enabled at configure time, and then you can enable it with an environment variable. This one's a bit harder to detect, so you do have to actually know that your machine supports SHARP to enable it. Another thing we have support for is Broadcom Rocky HCAs. So this is an alternative to InfiniBand, doing RDMA over converged Ethernet. And these are just some performance numbers from recent tuning we've done on Broadcom's adapters. So we can see up to a 20% reduction in point-to-point latency over OpenMPI and MVAPICH 237 based on the enhancements that we've done, as well as a 12 times improvement in MPI all reduce. And all of these designs are being brought into the latest MVAPICH Plus branch so that they'll be available as that one makes its way to the open source. These are some application numbers on the Broadcom HCAs. Once again, you can see that our Broadcom enhanced branch is showing some performance gains over both OpenMPI and older versions of 237. We can reduce up to 45% of the execution time on some applications, and we are bringing all of these designs into later versions of MVAPICH. So I mentioned earlier that with MVAPICH 3.0, we did add OFI and UCX support. So this is a significant change from our earlier versions, which had custom channels for each type of network device. So this makes things really easy. When you configure MVAPICH, you just set with device equals CH4 OFI or with device equals CH4 UCX. So now we don't have to do a separate one for IB, a separate for PSM, and then potentially different versions for OPX, Slingshot, Rocky, any of that. What we're going to do in the future is we are going to move to our own version of OFI level support for IB systems. So you'll even be able to drop the UCX version as well and just worry about OFI. You'll be able to build one version of MVAPICH with OFI support, and you can use any network that is supported by OFI. So in upcoming versions of MVAPICH 4, you will also be able to build both if you want to evaluate performance of UCX versus our support with OFI and our own provider. In MVAPICH 3, you set the provider by setting a MPI CVAR. This will allow you to switch between different providers that are given to you by the OFI library. Upcoming versions will be able to integrate natively with the OFI environment variables, so you won't have to worry about having two sets of variables. By default, we will use whatever library is available on your system. So if your system already has UCX installed or it already has OFI installed, we'll just link to that. Nice and easy, nothing you have to worry about. But we can also provide an embedded version, or you can build a custom version and link to that. So that allows you a lot of flexibility if you are moving between systems or you want to have different versions of libfabric with different features enabled or disabled. You can use one version of MVAPICH and you can link those at runtime. All right, so in terms of upcoming features in our mainline MVAPICH branch, we are going to be bringing in our OFI provider that has a unified design for both internode and intranode designs, and will support IB devices. So this will kind of take the place, if you're familiar with our older versions of our MREL device. We're going to essentially roll that into OFI, as well as enhance our intranode designs and bring in a brand new launcher that will support larger scale systems, as well as some enhanced features like moving our process binding over there so that we don't risk conflicting with different launchers. All of that will be making its way into the open source over the next couple of years. Some of this is already available in our closed source MVAPICH Plus library, which I'll touch on in a little bit. All right, so GPU support is kind of the big feature that makes MVAPICH 2 GDR distinct from our open source version. It's also what we're leading off with in the development of MVAPICH Plus. So MVAPICH 2 GDR and MVAPICH Plus are both CUDA-aware GPU libraries. So this gives us the ability to allow the MPI library to transparently handle GPU buffers in the same way it would handle CPU buffers with no input from the user. So rather than the user having to perform some kind of CUDA memcopy to move the GPU buffer onto the host, then send it via MPI, and then copy it back to a GPU, we can take care of that completely without user input in the MVAPICH library. And beyond that, we can do more advanced transfers like pipelining the GPU data or taking advantage of vendor-specific libraries like GDR copy without the user having to know how to do a GDR copy map and a copy that way. So all you see as a user is MPI send and MPI receive, and inside MVAPICH, we're going to take care of moving the data out of the GPU buffer, pipelining it as needed, and sending it across the node or across the cores and to the other GPU, all without the user ever having to worry about where those buffers are. So this gives us both high performance and high productivity for the users. So our MVAPICH 2 GDR version supports both NVIDIA and AMD GPUs. It has support for GPU direct RDMA for internode point-to-point communications. It has intranode point-to-point communication that can transparently handle both GPU to GPU, GPU to host, and host to GPU transfers, and can take advantage of advanced copy features like GDR copy for NVIDIA and AMD large bar mem copies. And it can also take advantage of CUDA and AMD IPC, or HIP IPC, to directly transfer larger messages between GPUs, and has optimized collectives for GPU buffers that can take advantage of all of these things in a collective specific context rather than just relying on the point-to-point technologies. So these are just a couple prerequisites for installing MVAPICH 2 GDR. Most of these are going to be pretty standard. The only one that we often see people missing is the NVIDIA PureMem module to actually allow for us to use the GPU direct RDMA, which is a pretty significant piece of getting the maximum performance. We also recommend that along with that, you have the GDR copy library installed. Otherwise, you'll see significantly reduced intranode performance. But all of this can be found in our user guide on our website. To install any of our closed source versions, but this is specifically targeted at MVAPICH 2 GDR, you are going to need to download an RPM from our site. These are specific typically to CUDA version and GCC or compiler version. If you don't see one that fits your needs on our website, we do have a form you can fill out and request one. We'll try to get that to you as quickly as possible. So we also have our CUDA-aware collective tuning, which is going to provide completely different tuning tables for GPU systems rather than CPU systems to take into account all the work that we've done on enhancing our GPU collectives. Yeah, and then this is just some of the features that we have in MVAPICH 2 GDR. The final version was 2.3.7. All of these things, as I mentioned before, are making their way into the MVAPICH Plus software stack, mostly starting with these GPU-specific enhancements. Couple tuning levers for our GDR designs. Most of these will apply to MVAPICH Plus. Some of them may see slight name changes, but all of the concepts will still be there. Most of our features are going to have an enable flag, which should be fairly straightforward. 1 to turn it on, 0 to turn it off. This can let you debug if you're getting errors in a specific message range. You can try disabling one of these advanced features and see if that solves your issue. Typically, it'll come at a performance cost, but often that can happen because either something's misconfigured on the system, or as we continue to see new systems come online, we haven't necessarily tested on that specific system, and maybe there's something unique about their installation. So most things can be toggled on and off with an enable switch, and then almost every range where we use these advanced technologies is configurable either with a range or a limit CVAR that let you tune exactly where you use these things. We're going to do our best to tune them for the general case, but any system where you use these could be different. Any specific application could be different. And so we do recommend that if you're not seeing the performance you want, mess around with a few of these, see if all of a sudden performance improves. If you don't know, reach out to us, and usually we can give at least an educated guess. So same basic principle applies for our GPU direct RDMA designs, and these are just some examples of performance improvements that we see with our MVAPICH 2 GDR designs compared to just a naive implementation of just copying data to the host, sending it, and copying back. Another feature of MVAPICH 2 GDR is our on-the-fly compression. So this basically allows us to improve the performance of very large messages being sent on GPUs. So GPU communication is often saturating the bandwidth of the network. And so this allows us to reduce the amount of data that we're sending through the network while still being able to achieve the same result. Many applications we found can tolerate some degree of loss, which allows us to use lossy compression for this and still come up with the correct result while significantly decreasing the communication time. So we can support MPC for lossless compression or ZFP for lossy compression. Both of these are bundled. Well, MPC is bundled with MVAPICH 2 GDR. ZFP we've also started bundling since MVAPICH Plus 3.0. And both of these can be used depending on how much, well, if your application can tolerate loss or not. Once again, enabled by an enable flag, and then has various tunable parameters to decide when we'll start using compression and what compression algorithm we'll use. If you're using ZFP, we have several other tunable levers for how we compress that data. So this just demonstrates some of the weak scaling results at the application level with our compression designs. And this is our all-to-all performance and performance with the deep speed middleware. We've also been able to optimize all-to-all performance by using IPC-based communications on GPUs, and that applies to both the micro benchmark and the application level, which you can see here with Hefty, and these designs are all available in MVAPICH 2 GDR. Our most recent version of MVAPICH Plus is also the 3.0 version, and like I said, we're working on bringing all of these MVAPICH 2 GDR designs into the MVAPICH Plus series. So this includes all of those point-to-point enhancements I mentioned, as well as the compression designs and the enhanced collective designs. What we're working on next in this series is, one, bringing it up to the 4.1 standard, as well as also bringing in some of those hybrid models that we discussed for MVAPICH 2X. We've also just gotten a beta release of MVAPICH Plus 4.0 that was made available late last week. This adds a lot of the features I mentioned for, this has all of those features for GPUs, as well as also providing a first version of our MVAPICH specific IB provider for libfabrics. So that can be set by using the mverbs OFI UCR provider. This is based off of existing support in OFI, but significantly enhanced based on our own experiences with the IB providers. It also adds support for Intel GPUs and includes all of those features that I mentioned for collective compression. So these are our GDR copy-like designs on AMD GPUs. As I mentioned, on AMD, it's called large bar. And we can see significant performance gains by using this, even up to very large messages. On the NVIDIA GPUs, we're restricted to fairly small messages for it. whereas on the AMD GPUs, because their bar memory is resizable, we can see these performance gains up to a much larger size. This is our performance. This is from the latest MVAPICH Plus 4.0 build on the Grace Hopper nodes with slingshot interconnects. And as you can see here, we are able to significantly outperform Cray MVAPICH with our enhanced intranode point-to-point designs. And we are performing even with them on the internode designs through the OF5 fabric. On collectives, once again, that is translating to our collective designs as well. Same with all reduce, where we can see up to an 80% performance gain on these cutting edge systems with our enhanced intranode performance. All right, so this is just a couple of quick case studies on our application level tuning and how we've been able to use some of these levers to extract the best performance from various applications. So the first one we're going to look at is the GROMAX application. So this was done while we were working on the Broadcom adapters. So initially, we noticed that we were getting really, really poor scaling at larger problem sizes. So we were able to take a look at the application performance with the tau profile and see where we were having issues in MPI. So what we noticed was that the performance was failing, or the performance was degrading when we started using the UD protocol. So for this application, we found that we could simply use RC all the way through by setting the hybrid communication threshold higher than the problem size that we were running. And by using RC protocol through the whole application, we were able to get much better performance. And as you can see, we saw about 2.5 times performance gain. Second one we're going to look at is the 3D stencil application. This just demonstrates the ability to tune the eager threshold specific to your application. So most of you are probably familiar with the eager versus rendezvous protocols in MPI. So once again, we were able to take a look at our performance numbers on this 3D stencil application and see that we were seeing a huge jump from 128K to 256K message sizes, which is typically where we see that the eager threshold, or is typically what we see as a good value for the eager threshold at the micro benchmark level. Clearly that wasn't the case in this application. So once again, we took a look at the application with the tau profile to see what was going on inside the library. And by tuning the eager threshold higher, using eager for all of these messages, we were able to get significantly better performance. Even though that is at the cost of a slightly larger memory footprint, it didn't really matter in this case. So in terms of where we're going in the future, as I've mentioned a couple of times, we are working on unifying a lot of these designs and enhancements in the MVAPICH Plus version, and then bringing as many of those designs as possible to the open source version. We're also exploring enhanced optimizations like we've done with GPUs for FPGAs, and integrating more features from newer architectures like the AMD Infinity Fabric that is found on a lot of the new Slingshot systems, Bluefield 3 adapters, and anything else that comes up in the next year, because I'm sure there will be. Funding acknowledgements from our sponsors.
Okay. So again, standing between people and coffee is never a good idea. So if there are questions that you guys have for us, again, these are all of our heroes. So as I mentioned, this is the work that has been done over a couple of decades by generations of students. All of us are here. So if you have questions about whatever Nat or I presented, feel free to reach out to us. And with that, we can break for coffee. We'll convene back here in the room by around 3:30 for our final session of the day. Thank you, guys. Let's thank Nat for the talk.